To project future climate with climate models, we first need a description of potential future emissions of greenhouse gases and other climate-forcing factors. And this depends upon how society will develop globally over the next century. Thus, scientists have created a range of development scenarios that have different implications for emissions. What are some of these possible emission scenarios, and what changes in precipitation and temperature would we expect to see under these scenarios? Please join us as we look at 3 extensively used scenarios and their significance in our understanding of future climate change. When climate scientists work with climate projections, they do so using possible development paths at a global scale. They refer to these possible paths as scenarios. There are several which have been used to describe possible future emissions, ranging from a modest increase to a rapid high increase. One family of scenarios, called SRES, refers to an important report, the Intergovernmental Panel on Climate Change, Special Report on Emissions Scenarios, which was presented about 10 years ago. The report describes 6 families of emission scenarios, of which the so-called B1, A1b, and A2 scenarios have been used most extensively. Let's look at carbon dioxide emissions as an example. The upper chart shows CO2 emissions for a range of SRES scenarios. Under the A2 scenarios, emissions continue to grow throughout the 21st century. The A2 scenario describes a heterogeneous world with regional self-reliance and preservation of local identities, continued population growth throughout the century, and economic development that is primarily regionally oriented. In A1b, the red curve, we see that emissions peak at about 2050 and then begin to decline. The A1b scenario envisions similar population and societal change, but with rapid economic growth and rapid introduction of new and more efficient technologies. On the other hand, under the B1 scenario, the green curve, with overall lower emissions, peaks a bit earlier than the A1b scenario, dropping to below 1990 levels by the end of the 21st century. B1 describes a world in which global population peaks in the mid-21st century. There is social and economic convergence among regions, and in which there is rapid change towards a service and information economy. The lower chart shows the effect of CO2 emissions on the concentration of carbon dioxide in the atmosphere. When CO2 is emitted into the atmosphere, some is absorbed into the oceans, some is taken up by vegetation that grows on the land, and some remains in the atmosphere. For the B1 scenario, concentrations begin to level out at the end of the century, at about 2 times pre-industrial levels. Likewise, concentrations begin to level out for the A1b scenario, but at a level that is about 3 times pre-industrial levels by year 2100. On the other hand, carbon dioxide concentrations under the A2 scenario are still rising rapidly at year 2100. So what do these different scenarios for greenhouse gas concentrations mean for future climate? This graph shows projected changes in global mean surface temperature that are obtained when climate models are driven with the 3 different SRES emission scenarios introduced in the previous animation, B1, A1b, and A2. You will notice there is also another curve, the orange curve. It shows projections of what would happen if concentrations could have been held constant at year 2000 levels. Let's take a moment to consider what the global mean surface temperature is projected to be under these 4 scenarios. The solid lines represent the average projected change from the models for each scenario, and colored bands represent the range of results from the models or the amount of uncertainty from this source. The solid blue curve shows the average projected change across all models that ran the B1 scenario. The year 2100 warming relative to year 2000 is about 1.8 degrees Celsius. The solid green curve and the green band show the same result for models that ran the A1b scenario. Under this scenario, the average projection for year 2100 relative to year 2000 is about 2.8 degrees Celsius. The solid red curve repeats this information for simulations using the A2 scenario. In this case, the average projection reaches about 3.6 degrees Celsius above the late 20th century. Under the constant concentration experiment, the orange line, there would still have been further warming, an additional 0.6 degrees Celsius more or less. A point to particularly note is that the responses to the B1, A1b, and A2 scenarios are not very different during the first 40 years or so. That's partially due to the fact that the climate is responding to past greenhouse gas changes, and partially because there is considerable inertia in the climate system that delays the response to new emissions. This means that we will have no choice but to adapt to a change in climate, even if our mitigation actions place us on a low emissions pathway, such as the B1 scenario, or even if emissions are stopped entirely, which clearly would be impossible. Remember that we now appear to be on the path that is closer to the A2 scenario. Now that we have some idea of how global temperatures might change, let's look at how precipitation, another important aspect of climate, is projected to change. The Intergovernmental Panel on Climate Change projects that precipitation increases are very likely in high latitudes, and that decreases are likely in subtropical land regions. These changes will have substantial impacts in British Columbia and internationally. For example, an average summer in southeastern BC will likely become drier, and in northern BC, summers will become wetter. The cool colors on this map indicate increases in precipitation, and the warm colors indicate drying. We see that Canada, including British Columbia, is projected to receive more precipitation in winter. Most of that will still fall as snow as opposed to rainfall, but the work at the Pacific Climate Impacts Consortium indicates that this could have considerable consequences for water resources in British Columbia. The black dots indicate where the large majority of climate models are in agreement on the direction of the projected precipitation change. That is, on whether there will be an increase in precipitation or a decrease in precipitation. Let's look at how precipitation extremes might change, on average, across North America, based on the A2 scenario, where emissions continue to grow throughout the 21st century. The vertical scale indicates the size of a 24-hour extreme precipitation event, from 50 millimeters, about 2 inches, to more than 90 millimeters. Across the horizontal axis are expected recurrence times for extreme precipitation events, once every 10 years, 20 years, 40 years, and so on average. The colored curves show the characteristics of extreme precipitation events, simulated by a global climate model over North America, and are thus generally not quite as intense as observed in real life. The blue curve shows that based on 1990 conditions, an extreme 80-millimeter precipitation event could be expected less than once in every 100 years, a 70-millimeter event every 50 years, and a 50-millimeter event every 10 years. The green curve shows the projected intensity of precipitation extremes in the middle of the 21st century under the A2 scenario. The red curve shows the projected changes by the end of the 21st century. Note that an event that would have been expected to recur once a century in the 1990s becomes a 70-year event in the middle of the 21st century and a 45-year event at the end of the century. What are the real-life implications of this? Suppose you are responsible for stormwater management in your local municipality. How might these future projections affect your job? How would you need to prepare? Storm drain systems are often designed for 50 or 100-year events, typically under current conditions. That means that if a municipality has designed its system with the 100-year event in mind, then it has in effect decided to pay for repairs and suffer damages only once every 100 years. In a future world, where intense rainfall becomes more frequent, this municipality will have to be prepared to make repairs and pay damages more frequently if it did not adapt its stormwater management system to new climatic conditions. Thus, the other option is to undertake an adaptation project, whereby the stormwater management system is adapted to the more intense future precipitation events. Here is another real-life implication of these projected changes in temperature and precipitation. Consider this example of what these projected changes may mean for agriculture in BC. British Columbia has many areas of rich agricultural land that yield world-class fruit and vegetables for us to eat and which are exported to other parts of the country. Growing degree days are a measure of the amount of heat energy that is available for plants during the growing season. For example, for a plant that begins to grow once springtime temperatures reach 5 degrees Celsius, a 6-degree day will contribute 1 growing degree day. A 10 Celsius day will give 5, and a 20 Celsius day will offer 15 growing degree days. The total for the season provides a good predictor of the state of the maturity of many crops at the time of harvest. Canola, which is currently grown in the Peace River region, requires about 1,000 such days to mature. The chart on the left shows in detail the number of growing degree days that were available in an average year between 1961 and 1990 throughout British Columbia. Note especially that much of the Peace River region has between 750 and 1,250 growing degree days on average. The right-hand chart shows a projection under the A2 scenario for the middle of the 21st century. It's derived from a climate change simulation produced with the Canadian Climate Model. You can see that a very large expansion is projected for the area that will receive sufficient growing degree days for canola. This example illustrates that by combining our climate modeling tools with detailed statistical analysis and other capabilities, we are able to bring information about the future impacts of climate change to users such as farmers at a fine detailed scale. What we can see from these scenarios is that the way in which our society develops will affect how our climate evolves, and that those changes could have some important impacts. Hopefully now you have a better sense of what each of these 3 scenarios is describing for our future, and the important role they play in helping us make informed decisions about how to progress as a responsible society.